third part is lithosphere definition and Earth topography. So we've seen that with barrel, we have the identification of lithosphere as being relatively rigid compared to the asthenosphere, relatively weak, soft. That's been also shown in that picture. So let's expand on that definition, first definition. So in terms of seismic waves, these are S waves and P waves, primary and secondary waves, with the velocity here in kilometers per second. And geophysicists identified that as these waves increase in speed from the surface and at depth until a depth of about 100, 150 kilometers, whereas there is a decrease in velocity propagation. So that's a low velocity zone. So that's another way to define this lithosphere-asthenosphere boundary. And why this low velocity zone? Well, one possibility is that at that depth, the geotherm, which is the increase in temperature in degrees Celsius as a function of depth, is reaching the solidus of peridotite, the rocks that make the mantle. And that here the solidus, that means the first occurrence of melt in the rock. And the presence of melt is going to attenuate seismic wave propagation. So that might be an explanation. In terms of mechanics, that's here represented in megapascal, the strength of the crust and the mantle as a function of depth. You see that there are two different ways to express the mechanics, the strength. Either a linear increase in strength as a function of depth, and at some depth there is a decrease in the strength that is parabolic. So maybe that's a part we can skip. I'm not sure who was exposed or not to rock mechanics. Everybody was exposed to rock mechanics or not? I can spend 5 minutes on that. So so you're not sure? I do it? Okay? Yeah. So that's stress, sigma, and strain, epsilon. So it's 1D stress-strain relationship. And rocks typically have, when they are submitted to stress, they have responded. The first response is an elastic response. It's not that big, but it's recorded by deformation. Elastic deformation is reversible. That means that if the stress stops, the rock recovers its initial state. And at some point, there is an elastic-plastic transition, which corresponds to this yield stress, which is the elastic-plastic transition. Plastic deformation is not reversible. It's forever. And rock typically then have a behavior where plastic deformation increases with increasing stress, with more stress being required to deform and so on. And then at some point, rock rupture. So that's a catastrophic loss of strength of the rock submitted to stress. That's the typical behavior. What is controlling this different state of strain? So pressure first. For pressure, with a pressure increase, that controls the transition from elastic rupture to elastic plastic ruptured and then elastic plastic. And the way I explain it, with the hands, is related to, so pressure is the depth of the column, of the rock column. So it's related to confining pressure. So if you put much pressure between your hands, it's easy to move. If you put a lot of pressure, difficult to move. So that's this effect that we measure here. Confining pressure. Temperature. Temperature, at low temperature, there is elastic, and then rupture. And at high temperature, you go from elastic to plastic without rupture. What does that express? Temperature, also with the hands. I'm a physics guy with the hands. I'm not really good at math. And with temperature, will allow atoms to be excited. And they move, as temperature increases, they move more. So it's easier to switch place with the neighbors. So this calls upon a process that is atom scale. This is rock scale. This is atom scale, the ability of atoms to move into the minerals. And that controls plastic flow. And as has been measured in laboratory, the brittle behavior, putting rock into a press, Byerly is a researcher that's allowed to identify the shear stress, normal stress, so that's the confining pressure, and that's the deviatoric stress. That's what controls deformation that is correlated to the weight of the rock column. And it shows that for any rocks, if you take a gabbro, a basalt, a granite, you have the same behavior with increasing strength as a function of increasing pressure. And it's almost linear. This is this part. And it doesn't matter if it's crust or if it's mantle. And then the other ones studied rocks at high temperature, and they identified that the flow law, so the strength as a function of temperature of quartz, here in orange, is different from the flow law of olivine. Quartz is the main mineral of the crust, olivine the main mineral of the mantle. So these are different. And they describe a decreasing strength with increasing temperature. And this is this part. So that's the law for olivine. And as the temperature in the crust here is not high enough to activate the flow law and the temperature of the crust, it's only here at that depth that it's activated. In the continental crust, continental lithosphere, you have the brittle behavior, which is related to confining pressure, both in the continental crust and in the lithospheric mantle. And there is here part of the continental crust that behaves, which behavior is controlled by flow of quartz activated by high temperature. And then flow of olivine activated by temperature here. So that means you have to have, well, first, that this low strength might correspond to the transition from lithosphere to asthenosphere. So without the need to call upon the presence of melt. Maybe just the high temperature deformation of olivine is enough to explain this low velocity zone and define the lithosphere-asthenosphere transition. I'll come back to the continental crust, lithosphere, sorry. There is a weak zone here, but there's also a weak zone here. So we'll come back to that in the lectures tomorrow. How important is this weak zone in tectonics and the construction of orogens? The definition of the lithosphere is here by density, so it's controlled by chemistry of the mantle. And this mantle has a history of extraction of melt, and it changes its density. And at first approximation, it's not that well defined, actually, but it should be more dense than the asthenosphere. And there's also then the kinematic definition of the lithosphere that makes plates moving relative to each other. So, in short, we have lithosphere, which is defined mechanically to be strong, thermally to be conductive. Oh yes. So when the rocks are strong, then it's not easy to deform. So heat is mainly transferred by conduction in these rocks. Whereas in the asthenosphere, that's the computation of Holmes that I showed earlier, it's possible that the mantle is in convection. So then heat is transferred by advection, not by conduction. So it's thermally conductive, chemically dense, and it's also kinematically identified compared to the asthenosphere. And all these characteristics, that's what controls plate tectonics and mantle scale mass redistribution. Okay, now, so that's the definition for the lithosphere. Now, how do we integrate the topography? So first we have to identify what is the behavior, the fate of the lithosphere along convergent plate boundaries, whereas it thickens homogeneously with the crust and then thins by gravitational instability, or whereas it behaves differently with homogeneous thickening of the crust and decoupling from the lithospheric mantle, where the lithospheric mantle is subducting. Seismic tomography has shown that most of plate convergent settings are associated with a blue zone that dips into the mantle. And this blue zone is a high velocity anomaly, which geophysicists interpret as being a plate. So most convergent, if not all, convergent plate boundaries are associated with subduction on one plate. Some are also associated with collision belts, some without collision belts, and this will be tomorrow's lectures. So it's mostly this behavior that we see. Not much this one. Which doesn't preclude this to be pertinent for the past, maybe the Archean and the Proterozoic. But at least for Phanerozoic, we know that this is the dominant situation. Earth topography. When you compare to the moon, what characterizes the Earth topography? Well, if you look at the moon, it's full of impact of meteorite craters. Do you see them on the Earth? Why isn't it the case? So I'm asking that to my first year students, and I identified a change in the answers since the last 10 years. So I'm curious to see what you have as an explanation. Why we cannot see meteorite craters on Earth? They say the same. But 10 years before, they didn't say that, with the idea that the atmosphere will stop the meteorite. You know, the stars, how do you call that? The light that is going across the sky. What is the name for that? I don't know the English name for that. Comet. No, but the ones that the one that goes across our atmosphere. They are small meteorites. They are not even very small, and you can see them penetrating the atmosphere. Do you think that the one that is causing a crater like this would be stopped by the atmosphere? No way. It's going to be creating lightning, light, by heating, but it's certainly going to go through. No, that's not the main process. Main process is activity of the Earth. The internal cycle, the external cycle, erosion due to presence of water, and plate tectonics that renews the Earth's surface, constantly. Continents, they are made of plains, mountain belts, basins, oceans of abysses, ridges, and trenches, and this reflects Earth dynamics, redistribution of masses owing to internal and external processes. And the moon is not a dynamic planet or body. The Earth is. Probably started like that, but all these craters have been erased from the surface of the Earth, all or most of them. So if we go a bit further into the Earth topography, you see that there is a big difference between continents and oceans. This is the altitude relative to sea level, taken as 0, and in classes of 1 kilometer, 0, -1, -2 kilometers, +1, +2, +3, +5. And you see the Earth's surface in percent that corresponds to each of these classes. So you see that there is a maximum for the continent that is between around 1 kilometer, so with an average of 800 meters. An average for the oceans that is at 4 kilometers depth, and there are two bell curves around these two maximum. So that means that probably the continents are distinct from the oceans. And this was identified by Wegener as well, you know, at the time of continental drift. So let's start now with the topography of the oceans. So this is the age map of the oceans, and compare that with the surface heat flux map reconstructed from surface heat flux measurements. What is the correlation? So as I'm doing it short, I wanted to ask you questions here, but need to speed up a bit. We can see that there is a correlation between the zone of high heat flux, that's 600 milliwatt per square meters, and the oceanic ridges. Oceanic ridges are zones of high topography in the oceans, which are zones of young crust. Oceanic ridges are zones of young lithosphere correlated with high surface heat flux. Oceanic trenches more or less corresponds to zones of old lithosphere that's very marked in the West Pacific, and it's marked by low surface heat flux. So there is a correlation between all these parameters, and this was calculated by Sclatter in 1981, that there was this decrease in heat flow as a function of distance from the mid-oceanic ridge and as a function of age. And he reproduced that by a cooling model. So, in other words, as the plate diverges from the mid-oceanic ridges, it cools. That's an isotherm, which is about 1350 isotherms. That becomes deeper and deeper. And when the mantle cools down, it becomes more dense, then it will subside, lower the topography. Ocean's topography is correlated to lithospheric thickness. As the plate diverges, the lithosphere thins and then uplift. And as the plate diverges from the ridge, it thickens, becomes heavier, and goes down, subside. Up to the point it's gravitationally unstable and boop, falls down into the deep mantle to make subduction. Okay, that's first conclusion. Oceanic lithosphere controls, the thickness of the oceanic lithosphere controls its topography. What about continent? So this is a map of crustal thickness that was compiled in 2000 by Basins et al. And you recognize what the main mountain belts are correlated with zones of orange, which corresponds to thick crust. So in mountains are correlated to thick crust. What about surface heat flux? You see that, so here it's a different scale from the other one. It's only going from 10 to 100 milliwatt per square meter. And you see a zone here, purple and red, that corresponds to alpine Himalayan belt, but also here to the North American Cordillera and South American Cordillera, which is all red, so meaning a high heat flux. Why is this high heat flux along mountain belts? I remind you, high heat flux in the ocean corresponds to thin lithosphere. For the continents, thick crust. Yeah, it means high temperature. Huh? High temperature.
The lithosphere is conductive, so it may conduct more heat. So that is why.
If it's conductive, it's actually insulating. The heat is better transferred when the conductive layer is thin. The more conductive, the less heat we'll get from the Earth interior. So it's the other way around. It's not a problem, but it was a good idea. We'll come back to that. So there's something missing. The continental crust is concentrated in radiogenic elements, uranium, thorium, potassium. So the thicker the continental crust, the more heat will be produced by these elements, and the hotter it will be. And this comes to the time scale that is required for having a high temperature crust after thickening. It comes to the time of heat conduction and the timing of heat production. And these takes about 10, 20, 30 million years to be efficient. It's not right away. If I take you and I put you at 150 kilometers, right away you'll feel the ultra-high pressure. It's instantaneous. But the high temperature will take 30 million years. The time of conduction, the time of heat production. But we'll come back to that. So, okay, possibly thick crust corresponds to high thermal surface heat flux, but there's also high surface heat flux in the East African rift. How do I explain this high surface heat flux? Rifting. Plate diverge, and what happens here? The lithosphere thins. So here, the high surface heat flux is explained by thin lithosphere. High surface heat flux here explained by thick crust. So we don't really know if here we're looking at an effect of thick crust, or we'll see. So let's first order observation. Thick crust, high surface heat flux. Rift, thin crust, high surface heat flux as well. So we have two explanations for high surface heat flux. So at first, surface topography in the continents was explained by isostasy. Mountains were identified by gravity data to be zones where excess of mass related to the mountain is compensated at depth by the deficit of mass. And this was actually, at first, it was a disappointment. Bouguer, who measured that in the Andes, he thought he could find a difference in mass related to the mountain, but he didn't find anything. So he was really disappointed. Actually, he described all this, but didn't find the model. The model came from these guys, Pratt and Airy, same year. One who stipulated that the zone of thick crust, the mountains, are related to low density material compared to the lowland where there is higher density. And that at some point, the excess of mass, because of the low density here, is compensated, and the pressure of this rock column is equivalent to this rock column at the isostatic depth compensation. This other model says that, okay, no, the crust has all the same density. It's just that beneath mountain belts there are thick mountain roots. To explain that at some compensation level, the pressure beneath the mountain belt is equivalent to the pressure beneath the lowland, and taking a density of 3.3 for the mantle and 2.67 for the crust. So that's this model. And it follows Archimedes' principle. Any object totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the fluid displaced by the object. So it means if we put the compensation level here, that means that the pressure in A is equivalent to the pressure in B. This is the crust, this is the mantle. What is the behavior of the mantle here? Where is the mantle in Archimedes' principle? You have it. Which part is it? Is it the object that is immersed, or is it the fluid? It's the fluid. What did I tell you about this mantle in terms of mechanics? That's the strongest shell of the Earth. And we are pretending it's a fluid? That's a big mistake here. It works. At first order, it works. But there is a big bias here. You can do that. That's exercise also for an exam, Malika. I provide exam for Malika. That's also something we can calculate. PA, pressure in A and pressure in B. considering the weight of the rock column rho g h, and you can compute the thickness of the root compared to the thickness of the topography, taking a normal thickness crust as a reference. Yes, so that's the last thing I want to show you before lunch. So this compilation of Artemieva and Mooney, they compile all geophysical data that allows to identify the thermal lithosphere and its thickness in kilometers, from 40 kilometers to 350 kilometers. What does this picture show? Well, first we see all the blue spots, a thick lithosphere, corresponds to old cratons. The Superior Province, the West Africa craton, the Scandinavian, Siberia, somehow India, West Australia, South Africa, the Brazil. We see all the cratons. And they are related to zones of low surface heat flux. And that's because of the thick conductive layer that impedes heat to be transferred. Right? It's insulating. Matches? Right? When the lithosphere is thin, convection is very efficient at transferring heat. Look at what happens in the Alpine Himalayan belt. Red and orange. A lithosphere that is 40, 80, 100 kilometers thick at most. Lithosphere. So if you take out 50 to 60 kilometers thick crust, it only leaves 20 to 30 kilometers for the lithospheric mantle. So in zone of thick crust, for the Alpine Himalayan belt, the crust is thick, the lithosphere is thin. We have a big paradox here that we're going to resolve in the next lectures. So if you take that into account, we don't know if most of the high heat flux identified here correlates to thick crust producing a lot of heat by radiogenic decay, or thin lithosphere that promotes transfer of heat by advection, and maybe both. So in other words, same for the topography. How much does it relate to thickness of the crust? So a thick crust will promote high topography, but a thin lithospheric mantle, what does it promote in terms of topography? Thin lithospheric mantle, uplift. So if we want to understand continental topography, we need to consider both the thickness of the crust and the thickness of the lithospheric mantle. So this leads me to my conclusions. So I'm not going to go through that. I'll leave that also. Yeah. Let's see. So the topography of the ocean is controlled by the lithospheric thickness. The thicker the lithosphere, the lower the topography. The topography of the continent is related to the crust lithospheric mantle ratio. The thick crust promotes high topography, but if it's associated with a thick lithospheric mantle, that would counterbalance the effect of high mountains and lower the topography. If a thick crust is related to thin lithospheric mantle, this will increase even the surface uplift. And in rift, it's both thinning of the crust and thinning of the lithosphere, and you also have a counter actions of these two processes. And I'll leave you with that slide that introduces the lectures of tomorrow. What about topography in zones of plate convergence? So I just did that with Google Earth. I did the sections across convergent plate boundaries, and you can easily retrieve the topography. So I did that for orogenic wedges, zones of mountains with a triangular shape. Wedge is a shape. A wedge is a triangle. So I did that Taiwan, Papuasia, Ecuador, Patagonia, Pyrenees, Alps, all roughly triangular. Oh, by the way, by topography, I do not mean morphology. I leave that to geomorphologists who are studying erosion and surface processes. topography is the first order shape. That's this shape, and then it's been eroded a little bit, valleys and peaks. That's morphology. So you have triangles, but you also have rectangles, what we call orogenic plateau. Altiplano is one, Tibet is another one, and there's also one in Anatolia. In Turkey, there's another plateau. And more surprisingly, there are intermontane basins. The basin and range that I talked about, but it's also the case in the Pannonian basin between the Dinarides and the Carpathian, and also in the Zagros, you have basins, low topography, surrounded by high mountains. So that's surprising. And if we look at the altitude difference between different orogenic wedges, as a function of width of this orogenic belt, all the squares here are the orogenic wedges in green, and you see that there is somehow a correlation between altitude and width, up to something about 5,000 meters, and there's no longer a correlation between altitude and width. This corresponds to the wedge plateau transition. What limits the altitude of orogenic belts? What controls that transition from wedge, from triangle to plateau? So this is tomorrow's lecture. You have the night to think about it. Okay, I'm done.